Okay, so this picture you should remember in your head. So the molecules can be represented by this kind of diagram. When we represent an orbital, as I said, the orbital will draw like this. When you want to represent the whole molecule, you put a picture like this. And in this picture, these two centers represent the two atoms, and this one represents the vibrational levels. The note is, to go from here to here, it requires certain amount of energy. To go from here, 1 to 2, requires certain amount. As you go up the ladder, the gap gets smaller and smaller, and eventually it becomes degenerate and then breaks. Okay? This is a normal picture they use every day in understanding molecules. All right, so let me see what else. Okay, now I want to go back the whole thing what we talked today, and I will ask some questions. Let's see whether you know what is the answer. Okay, so we talked about a whole bunch of things. Tell me, what are the basic laws of photochemistry? I talked about this morning. If you are going to do a photochemistry, what you should know? That is these two guys. I said something. This is called the Grothus Druper first law of photochemistry. Tell me what exactly you got. The people, some of you are here. I think most of the people who are here are there in the morning. Most of the people who are not here probably disappear. So what do you remember this? What is basic? There are two things which are very important for a chemical reaction or for anything to happen, whether you want to see a fluorescence or whether you want to do a chemical reaction. What are the two things that are important? Okay? You can discuss and then tell me. Between you can talk and then you can talk and then let me know what is the answer. It is pretty easy, straightforward. It is there in the notes. Okay, tell me what is the law number 1. You can read. Okay.
What's the question?
Huh?
That question.
The question is, what are the 2 important things that you should know before you do any experiments with the light?
The light must be absorbed
The light must be absorbed by the molecule. Okay. That is one. That means you should know the absorption spectrum of the compound. So you should know where the molecule is absorbing so that you can use the appropriate light to activate the compound. That is important. What is the second important thing? I cannot also read, okay? This is pretty fuzzy for me, for you. So what is the second most important thing? Huh? Okay. So the second most important thing is, if you want to activate 100 molecules, you should have at least 100 photons. You cannot hope that the photons you can split and then give it to 2 different molecules. the one photon doesn't get split into 2 or 3 smaller things. So either they all stay together as one. So if you depending upon how many molecules you activate, so this is what is here. So this one, each photon of light is absorbed by only one molecule. So if you have more than one molecule in your flask, then you need more than one photon to activate that all the molecules. Okay. Right. So let's see what else. Okay, tell me what is the light that we talk about? Is it a particle, or is it a wave, or is it both? Both. Okay, so we went through this one. We said the light it can be a wave or it can be a particle, depending upon with which it is interacting. If you want to define the light, what is the primary important factor? What is the thing that you have to know to tell whether this light is blue or green or red or something? How much energy it has? What is the thing that you will use? Okay. The answer is the one that I have highlighted there. So if you want to define a photon, if I want to do a reaction, or you want to irradiate a compound to see the fluorescence of a compound, then Dr. Leaping will tell you irradiate at this, use this light to activate your compound, and you will see the fluorescence. So what is the number or something that you will write down to activate a molecule? Wavelength. Okay, so wavelength defines how much energy particular photon has. Okay. Suppose you have a wavelength of 700 nanometers and then another one of 300 nanometers. Which one has got more energy? Okay. So you have the light of different wavelengths. So 700 and 300. The 300 one has more energy than the 700 one. 700 nanometers has lesser energy compared to 300. The energy of it is controlled by h mu. Mu is hc divided by lambda. H is fixed. H is Planck's constant. C is the speed of light divided by lambda. So division between 700, the number is going to be smaller. If it is 300, the number is going to be larger. It will have more energy. Does it make sense? Does it make sense? Okay, let's see. I will put this here. What happened? Okay. Okay. Can you tell me what is Born-Oppenheimer approximation? This guy. Okay. Tell me what is Born-Oppenheimer approximation? What is that?
Electron vibration faster than current with wave vibration.
What is Born? That is this Born-Oppenheimer approximation that we use, in calculating the energies of a molecule. That's it. In quantum chemistry, if you want to calculate the energy of a molecule, you make a major approximation. That is what we call as Born-Oppenheimer approximation. Okay, what is that approximation? Okay, when you think of a molecule has got at least 3 different things. It has got electrons moving around, and then it has got atoms always shaking around, and the spin which is exchanging. So, if you want to define a molecule, at the same time, you have to know the positions of the nuclei, positions of the electrons, and also the spin of the electrons. But it is not possible to know all 3. Because all the time everything is moving. So it is like everything is always moving around. So if it is moving around, there is no way you can calculate the energy of the molecule. To do that, to calculate, what we do is, it is not completely moving, it is staying like this. And then for that particular arrangement, you calculate the electronic configuration. But if you calculate this energy, it is not correct. Because molecule is always doing something like this. But if it is always doing something like this, you cannot figure out where the electrons are. So what we do is, okay, it is staying like this, and you calculate. Because that is what is called as the Born-Oppenheimer approximation. So you can make it as though the molecule is stationary, and you can calculate everything, and then you can slowly adjust your numbers, assuming it is moving. That is possible because the speed with which electron moves and the nuclei moves, the spin change, they are all in different time scales. So the fastest is the electrons. So when the electron is moving from one place to another place, the nuclei will not change because electrons will go in 10 power minus 15 seconds. For this to move, it takes 10 power minus 12 seconds. So if you assume the nuclei is stationary and then the electron you move, so that the assumption is correct. But when the thing is moving a little bit more, then you will have to readjust the original number. So that's how the calculations is done. If you say that everything is moving, so I don't know, I'm not going to calculate anything, that means you will not know anything. So the assumption is a very major assumption, but it's very useful assumption. It's called the Born-Oppenheimer approximation. When you take a physical chemistry course or quantum chemistry chapter, you will come across this term. Okay? Okay, so let's see what else. So, I already was mentioning the time scales in chemistry are very important. Because the lifetime is how long a molecule lives in the excited state, or how fast it reacts, is controlled by the time change. For example, singlet and the triplet, they have different time scales. For example, if you take a molecule, put it in the singlet state, where the 2 electrons have opposite spin, and then you put another molecule in the triplet states where the electrons have the same spin, they live for different time. That means from there to come back down, for singlet it will be faster, for the triplet to come back down it will be a little bit slow. Tell me which one will have a longer lifetime. Lifetime means how long it lives in some place. Okay, you take a thing and then throw it out, for the singlet. Another one you throw it, goes to the triplet. Which one will come back to you faster? Singlet or the triplet?
Singlet.
Singlet. Okay, good. So singlet will come faster. that is singlet always have a shorter time scale, that is in the nanosecond, 10 power minus 9 minus 10 seconds, whereas the triplets will have 10 power minus 6 to minus 3 seconds. So tell me why singlet has a shorter time scale, triplet has a longer time scale. Why the triplet is longer, singlet is shorter. So we didn't talk about this before. Singlet means the two electrons have opposite spin. So if the electron wants to come back from the one orbital back to the other orbital, it doesn't have to change the spin. All it has to do is it is to go from that orbital back to the original orbital. If it is the triplet state, the two electrons have the same spin. So go back to the ground state, they have to have opposite spin. So to take the spin from one alpha, shifting it to beta, it takes some time. So usually what happens is the triplets will stay there longer because it has to find a way to change the spin, and it will take like 10 power minus 3 to minus 6 seconds. Whereas for singlet state, that's not a problem. It just comes back very quickly. Okay? Okay. When you say triplet, how many states are there in the triplet? So when you have triplet, are there 3 different configurations or only one configuration? How many? Including spin. Or these 3 states when you write, we say S0, S1 and T1. We call them as T1. When you fire one line, T1, does it have 3 different lines or is it only one line? The answer is see, we could always, when you any book you see here, you will see a triplet. We similar to put like this. Is 0, we will put S1, and then we will put T1. So this one is assuming here we don't worry about the spin. Suppose we worry about the spin of the electrons. Singlet, how many states? Triplet, how many states? Triplet means 3. So when you have the triplet, the 2 electrons with the same spin, they will have 3 different spin states. That is alpha, alpha, beta, beta, and this one. So this triplet state, normally it has got 3 different states. So in fact it is actually looks like this. So the separations is very small. It will be like 0.5 kilocalories or even lesser than that. So we don't worry about it. So we just put as a single line. That single line that when you say triplet, there are 3 states in that. But these 3 states, if they are almost degenerate, they will be equally reached. But in a magnetic field, you can separate this into 3 separate states. Okay. Suppose you have n to pi star and pi to pi star. Which one will have the larger singlet triplet gap? N to pi star, pi to pi star. Which one? The gap between the S1 and T1, which will have larger? which one will have a larger gap? You just answer this one you went through different.
This one.
Huh?
This one. This one.
Yes, one? No. Singlet triplet gap, n to pi star or pi to pi star, which of these two will have a larger gap? Between the S1 and the T1, it is n to pi star. Another molecule with the S1 and T1, which is pi to pi star, which of these two will have a larger gap?
D1. This one.
Huh?
D1. This one. So, larger.
No, I think the question is, so if you have n like a, if you have the electronic state, if you have the n to pi star electronic configuration, the energy difference between n pi star, which is singlet n to pi star, corresponding to triplet n to pi star, that is a singlet and triplet, and you have another molecule, pi to pi star singlet, pi to pi star triplet. So the gap between the singlet and the triplet, which of these two will be larger? Okay, so how many people think it is pi to pi star? One. Yeah, okay, I counted you. Anybody else? Which one? If you say pi to pi star, just raise your hand. So from there, at least I know.
Pi to pi star is larger than the
Huh?
pi star.
What's that?
Pi to pi star is larger than the n to pi star.
Okay.
Pi star.
Okay, so you, number two people agree, three people. So anybody else? Okay, so pi to pi star will have a larger gap. Because we were, I explained this picture here before. Because if you remember, we said the gap is the larger the overlap, the larger the gap. So n and pi star, they are not overlapping that much. So the gap between the singlet and the triplet is smaller compared to the pi to pi star. Okay. All right. So now I think I want to start something new. It is slightly different from what we talked about. It is about absorption and emission. This is something which is very practical that you probably, some of you might be doing every day. Emission, fluorescence, phosphorescence, all that kind of stuff. Okay. So do you need a gap, some 5-10 minutes, or we just go over? 5:50 we will stop, whatever happens. Okay, around 5:50. Now it is 4:30. You are all tired? Because almost 6 hours, we're talking the same things. So it is too much of photochemistry in one day. Okay. Huh? You want a gap? What is that? Okay. Okay. Yeah? You want a gap or no? Yes? Okay, we'll take about 10 minutes, 4:45. We'll meet again. Okay. I know it's pretty long. I don't like these 6 hours. I cannot stay here for too long. I also want to go back to Miami. So 4:45 we'll talk about it. Okay, all these cups are, you can throw all the cups and water bottles.